It's my great pleasure to introduce our distinguished speaker, Professor Niayesh Afshordi, a renowned cosmologist and theoretical physicist. Niayesh has made groundbreaking contributions to the field of cosmology and quantum gravity and astrophysics. He comes to us today from the Perimeter Institute for Theoretical Physics, and he's also a faculty member at the University of Waterloo. Niayesh did his undergraduate in Iran.
That's right.
And then came to the US with his PhD at Brown University, where I had the privilege of sharing a PhD advisor for a short amount of time, Robert Bradford. He finished his PhD though at Princeton with David Spergel. He then went on to do a postdoc at Harvard, and then a postdoc at the Perimeter Institute, which turned into a permanent position where he is now. Today, well, he's written a book, right, called The Battle of the Big Bang, co-authored, and today he's going to tell us about quantum black holes and cosmic causality. So please give a warm welcome to Niayesh.
Thank you very much, Damien. Yeah, very good. Thanks a lot, Damien. It's a pleasure to be here and meet many of you for the first time. Also, it's reunion of some kind with many of you. So Damien, in fact, when my wife and I first started at Brown University 20-something years ago, 26 years ago, Damien was there as well, and yeah, we kept reminiscing on the old memories there. And many of you here, we crossed paths over the past few decades. So it's an amazing place. My first time here, so I'm having a lot of fun, and I hope to get to meet more of you and get to chat about any of these. I'm happy to have interruptions and questions throughout. So if you want to stop me and it's something you cannot stand until the end, please do interrupt, or you could ask the question there. So the purpose of this talk is to provoke you, to invite you to be outraged about the state of the cosmos and physics and society and everything. So it's inviting you to rebel against the regime, against the system. And that's the way it's going to start. And hopefully by the end, you're going to be convinced that you're going to join the revolution. Okay? But it all starts from quantum black holes. And I want to try to convince you that all that you've been taught about causality in physics might be fundamentally flawed. And maybe that's what needs to be revisited if you want to make progress in fundamental physics. So, if some of the things that you hear from me don't sound heretical, I assure you it is. So, I'm going to start with the introduction about the crisis, the state of crisis, as various things in. They're not really. Then I'm going to talk about echoes, gravitational waves. I'm going to talk about what quantum black holes may look like, what lies beyond their horizons. And I'm going to come back to cosmology, where I started from. So, the crisis in physics. So, many of you are students of physics. You're being taught about the great successes of physics in the past century. I'm here to tell you that your professors are wrong. Physics is in crisis. When we add quantum mechanics to relativity, there are two cornerstones of modern physics. You end up with infinities. You have singularities that don't make any sense at the hearts of Big Bang and black holes. You have information that is lost when black holes evaporate. You have this dark energy, this very dark energy that everyone tells you is there, but somehow it's 60 orders of magnitude smaller than our predictions. And then there is this so-called best theory of nature, which is not natural for some reason. A standard model of particle physics. So this is a strange time to live in, that we have enjoyed great success, but a great crisis in fundamental principles of physics. It's not that people haven't tried to solve these or attack these problems, it's just that all their proposals are not testable. So I call that crisis of falsifiability. So we have great proposals with very smart people, but none of them can be tested. So string theory predicts, amongst other things, the landscape of 10 to the 500 vacua. It doesn't tell you where we are in that. So many predictions, one of them will probably be right, but is that okay? There is no signature of any of fundamental assumptions of string theory, supersymmetry, anti-de Sitter space, or extra dimensions. These are all the things that you need to actually make sense out of string theory. And it's not just the string theory. Any proposal for quantum gravity, and there are dozens of them. So many of my colleagues at Princeton PhD work on that. None of them have concrete testable predictions. So I like to criticize everyone on an equal basis. When you come back to cosmology, inflation, which is the most popular and most well-studied theory for the origin of the Big Bang, can fit any data. So over my lifetime and Damien's lifetime and many of all the professors here, there have been many observational data come and gone. They detected curvature, and then we realized that it's not there. We detected gravitational waves, decided that they were not there. Detected non-Gaussian, decided they're not there. And every time there was an inflation model that fit them, and then of course when the data went away, there was another inflation model. So it does seem like something that cannot be tested or ruled out, because there's always no matter about the data that says an inflation model that is written. And the question is that are these theoretical physics or your best guess for the fundamentals of theoretical physics? Is this turning into a religious dogma? This has to be it, as opposed to something that you can actually test it. So, and here's that, there we are, with crisis in physics. You have our physicists who are sitting here. On the one side, we have nature that we, at the fundamental level, we need to understand it and explain it, but we're getting in trouble in terms of understanding the fundamental workings of nature in terms of quantum mechanics and gravity. On the other side, we have the society who started to think whether we really need science or scientists are actually helpful. And that's and these are interconnected. I think that we have trouble dealing with nature and trouble justifying our existence in society that doesn't necessarily see the value of fundamental science. So how do we go about this crisis? And so I'm just going to give you more evidence of the crisis. So those of you who don't know this gentleman here is Chris Stokes, who's a professor of physics and astronomy at Harvard. He was a dean of science at Harvard until last summer, a good friend of mine. He visited Perimeter more than 10 years ago and gave a colloquium. This was the title, The Dark Energy Crisis and the Prospect of Intellectual Stagnation. Right, so sounds pretty good. He predicted the scenario for the future of cosmology and physics, dark ages. So, compared it to dark ages, which is a term referring to the period marked by cultural, intellectual, and economic deterioration. Sounds familiar? Followed by intellectual and religious intolerance, stagnation, and poverty. That's not. And then this was his prediction that if measurements continue to favor W-1, that's a cosmological constant, no deeper theoretical ideas emerge, and then LHC gives vanilla Higgs and little else. So that has come to pass. We discovered Higgs and haven't discovered anything else. Then things look bleak. It will be difficult to extend existing techniques to milli-W level, which is just saying that we cannot do much for the dark energy. Which is kind of where we are. In fact, I emailed him last summer and I'm really tired to congratulate him and ask him whether he still agrees, and he thinks that we are in this crisis mode right now, the dark energy crisis. Okay, so Other colleagues of mine have their own takes on the crisis. This is from the particle physicist, my friend Sabina Assenfelder, who used to be a parameter, and the physicists are lost in math. He losing the Nobel Prize. This is when he discovered gravitational waves from the Big Bang, and then undiscovered them. And to my friend Leo Smolin, who has his own take on the crisis fundamental physics. And this is most recently, a couple of months ago, this is a podcast with Lenny Susskind, who's father of string theory, and he also described the state of string theory as in crisis. So here we are, but as some of you know, this good Canadian who passed away a few years ago, famously said there's a crack in everything, that's how the light gets in. So our job is to find the crack, and then the rest of life will do its work. So where is that? So I'm gonna try to tell you where that crack is, and then hopefully the light will get it. So the thesis of this talk is that crack in this facade of modern physics is causality, in particular cosmic causality. And by cosmic causality, I mean this causality on the scales of places where we think quantum gravity should become important, places where we push quantum mechanics and gravity to their extremes. So that's where I want to argue for you, or try to convince you, that's where causality, our very notions of causal effects, are going to start to break down. And understanding that breakdown may be our clue or our hint to a more complete understanding of fundamental physics. So what does this mean? So this is the simple question: how can information travel across these horizons? Theory of relativity teaches us that there are these things called horizons, and information cannot cross them because that requires them. It requires information to move faster than the speed of light. And according to Einstein, but he used it as a foundation of theory of relativity, nothing can go faster than the speed of light. So information cannot travel faster than the speed of light. However, we have these two situations. We have the cosmological horizon, which seems to be uniform on a scales that are super horizon, much bigger than the And then we have this situation of black hole, a different situation, which we have event horizons of black holes, but somehow information needs to get out of them if they are to evaporate. If you don't want to destroy information. So these are seemingly different situations, the cosmological horizon and black hole horizons. But they both seem to point towards something which goes to the heart of relativity, and that's the nature of causality in our universe. Can information cross the horizon or not? Okay, so with that introduction, I want to tell you about concrete steps where you can take to kind of unravel or clear up what the status of causality in realistic objects we have in the universe. So I'm going to start from the black holes. I'm going to talk about something that you may not have heard about, the column echoes of the black hole. So the story starts from some weird terminology known as a firewall. But if you don't like that terminology, you can just think about Hawking, the late Stephen Hawking, and this is actually the 50th anniversary of discovery of Hawking evaporation, or I'm not exactly sure which, or it's basically his discovery of information paradox. I think it's the 50th anniversary of evaporation, if I remember correctly. And so the big conundrum was what happens to the information when black holes evaporate? Because if the information is to get out, they need to get out of their horizon, but then horizon nothing is supposed to get out. So people have kind of changed their minds over decades about this paradox. But one of the more recent versions of this paradox due to these gentlemen, Mary Harold Kuczynski and Solid, but earlier arguments with Samir Masur, who's another good friend of mine, and was saying that basically, if you want evaporation of black holes to work the way Hawking suggested, that black holes actually evaporate, but at the same time, we want horizons of black holes to be smooth places where you can trust a space-time picture, classical space-time picture, or they just smooth. That's the kind of assumption, the so-called monodromo assumption. They cannot be consistent if quantum mechanics is a right theory, if the quantum mechanics is valid. And they had a solution that, of course, you could suspend quantum mechanics. You could suspend the Hawking picture of the black holes, maybe black holes will evaporate. Or the third option, which they advocate for, is the so-called fireballs, that horizons are not classical. Weird quantum stuff happen at the horizon that are kind of drastic. So observers burn up in quotation mark as they hit these fireballs. So that was their argument, and there have been many arguments since about what is the nature of this paradox. But I mean, there are different takes on this, and we can kind of discuss this as a separate talk on this. But I'm going to kind of all the proposals that people have violate one of the assumptions in this fireball paradox, and each one you want to violate is kind of depends on who you talk. For example, some people think quantum mechanics is violated. Many of the relativists, famous relativists, wow, think that maybe quantum mechanics is violated, or that black holes will have entropy according to the entropy laws. I mean, entropy laws in fact is one of the assumptions. So, the great news is that these are not just abstract discussions, these are things that we can now test. And that's thanks to the discovery of gravitational waves. So we now measure these gravitational waves, and we can simulate the black holes merging, and the predictions of the simulations for the gravitational wave is more or less consistent with that observed by LIGO experiments. There are a few hundred of these that are not detected by LIGO experiments. The prediction, and I'm going to try to convince you, is that if there is new physics happening at the horizon of black holes, it's going to show up in the so-called delayed echoes in these gravitational waves. Okay. So I'm going to talk for the next 10 minutes about these echoes, but the motivation for them and what is observational critical stuff. So this is my favorite argument for echoes. It's not very well known. I hope maybe it will be better known now. But it kind of goes back to Hawking's derivation of black hole evaporation. So if you have a black hole, Hawking argued, based on laws of quantum field theory, in terms of space-time, that they should radiate. If there's nothing falling into them, if you put them in vacuum, they're going to lose energy through quantum effects, basically, by solving quantum field theory in terms of space. If you think of black holes now, Hawking's calculation was for classical space-time, but if you think black holes are really quantum objects, which is that's what we would expect in a quantum theory, then evaporation of black holes through a Hawking process would be akin to a spontaneous emission that happens for an excited atom. Because I mean, how else would something emit photons, a quantum object? It must be excited, and as it gets lower and lower state, it would emit photons or other particles. So spontaneous emission is Hawking range. So then you could ask, okay, so take this quantum object and follow basically what Einstein did when he derived the spontaneous, he derived the relationship between a spontaneous emission and a stimulated emission in his work. So what Einstein showed, and it's something that you can prove in, you do quantum mechanics, you do quantum perturbation theory, which the Fermi's golden rule. we can show that basically if now you put these quantum objects in a bath of radiation, then this emission can be stimulated in a manner that's proportional to the intensity of incident radiation. So if you put these quantum objects, this excited atom, in a bath of radiation at the same frequency that it would be emitting in vacuum, then its spontaneous emission is stimulated and it would basically be excited faster than it would have otherwise. And in fact, we could use this principle, assuming that perturbation theory is applicable, the same way that we do in quantum mechanics, to derive a reflectivity for the horizons, which is basically a Boston factor, e to the minus h bar omega over k. T by Th is basically the temperature of this incident quantum. So this derivation is basically exactly follows what you have in this paper. Now these are both German papers, but you should recognize both of these. The one on the left is Einstein's paper from July 1916, where it's basically emission absorption quantum radiation, and it's basically where he established a relationship between absorption, spontaneous emission, and stimulated emission. And in fact, this relationship between these two in thermal equilibrium is what he used to establish the ratio of these two processes, like absorption and stimulated emission. And at the same, basically within a couple of months of each other, within 6 months of each other, so 6 months before this paper is published, Einstein actually published his Einstein equations, which describe essentially led to prediction of black holes and prediction of gravitational waves, and which was triumphantly confirmed. So within 6 months, Einstein's mind was imagining quantum radiation processes and the laws of gravitation. And what I'm looking to is that if you put these two together and you basically follow the chain of argument, you end up with this. And there are assumptions, of course, it's not 100% proof, but you end up with this result that horizons are not really black, but rather they can reflect frequencies that are low. At high frequencies, reflectivity goes to 0. So black holes are black at high frequency. But at frequencies comparable to gravitational waves, they could have significant reflectivity. And indeed, these are the frequencies. The frequencies at which we see gravitational waves are comparable to the Hawking temperature. So these are the frequencies where we should expect to see these reflections. So that is the proposal. And this is a proposal that the past 10 years, many of us have been very excited about. So this idea of stimulating Hawking radiation, my former postdoc, Vainu Bappu, now he's in Kyoto, and Vainu, my former student, we showed it for the first time back in 2020. Earlier, a time scale for these echoes was also pointed out. Basically, the idea is if you have your quantum structure in the horizon, and then you have the standard classical graph with the so-called angular momentum. Yes. Yes.
How physical object of the compact? It has some bulk modulus, some love numbers, and it's just following relaxing.
Right. Very good. So this derivation of Hawking temperature is only for objects that have classical horizons. So if you have a neutron star, there is nothing equivalent to for them.
But what about these sort of non-singular black holes with the modular one-time object or things like that?
I think that's a good question, and then I think the question is to what extent do we understand the properties of the fluids that make result, like viscosity and various properties. But yeah, indeed, if you want to describe a black hole as a fluid, this interaction in this environment depends on the transport coefficients of the fluid, like viscosity, and those can tend to answer.
So this will give you sort of distinct predictions or the title of the
Yes, that's right. Absolutely. Yeah, in fact, the tidal log number is similar. I mean, the log number goes to zero, this reflectivity goes to zero. So there are papers that establish relationship between the log number and this reflectivity, which is in fact frequency dependent. Okay. Yes.
I just had a quick question about the derivation of how we were essentially paralleling the derivation of A and B coefficients.
Yes.
For gravitational.
Mhm.
So when I did derivation of A and B coefficients for stimulated emission, he gave me some sort of detail about.
That's right. Yes.
But it seems like in gravitational, in a collision of two black holes, that's a highly non-equilibrium process.
Right, absolutely. So so this is the part that I mentioned, the perturbation theory. And the end point of the measure of black holes is kind of this range, or I can make a better picture of this range. So what people use to describe this is linear perturbation theory, the so-called ring down phase. So it is thought to be a perturbative process, at least in some sense. Now, whether it's the right sense is still it's an open question. But in some sense, it's a perturbative process. So yes, the whole merger of two black holes is not perturbative, but this ring down, which is the end phase, we could use perturbation theory to describe it, and there's good evidence. Then the question is, it is thermal equilibrium. And so basically one thing that Hawking showed, and others have also shown, is that if you put this black hole in a thermal mass of Hawking radiation, then it will be in equilibrium. Right. So because the evaporation would cancel the absorption. So one thing you can rigorously show is that this black hole will be in equilibrium with the mass of Hawking radiation. So you could use that to establish what is the ratio of a stimulated emission to absorption at any frequency, because you want to have detailed balance at any frequency. But then you take that and you say, okay, what if now I pump up this incident radiation to much bigger values? Then you won't have equilibrium anymore. But you could still use the same ratio. So you establish this reflectivity in the situation where there is equilibrium, but then use it when you don't have equilibrium. Now, someone may argue that this reflectivity may change, but then that's not a perturbative. So that could be like a nonlinear optics thing, right? Which can happen, and I think that's certainly a possibility. But in the perturbative regime, this is, you use it, you can drive an equilibrium and an upright gravity. So it's basically a linear response. Okay, but these are very good questions. And there are loopholes, and there are more technical loopholes that I'll be happy to discuss with you. So this sets the amplitude of the echoes, this reflectivity, but there is a time scale of echoes, which is basically the time it takes for you to reach this membrane or fireball and then get reflected back, and then this is like a basically cavity that is established here, or an echo chamber. And the time it takes basically to travel between these two boundaries, one is a classical gravity. This is basically the light ring where the Van Horizon telescope sees this image. And this is the quantum object, whatever quantum effect that solves the information paradox. The time scale is long, but it's not very long, it's only logarithmically long. And the reason is that basically it takes infinite time to reach the horizon, but if you are limited outside the horizon, it's only logarithmically big, and logs are never very big. So you end up with a time scale which you will predict very precisely, even though we don't exactly know what the scale of quantum gravity is. So if you change the scale of quantum gravity by 4 orders of magnitude, it changes this echo time only 3%. So this is great. This is a concrete prediction. We have an amplitude, we have a time scale. Are there these echoes in data? That's a good question. Of course, this is the worst nightmare for a theorist, of course, because if you don't have any tunable parameters, and then observers go and see it, they're going to rule out your theory. Now, before I show you that, I'm just going to give you another argument for why you expect echoes, and this has to do with essentially entropy. So if you just take classical black holes with horizons that's kind of are classical, what happens is that you kind of fill this cavity inside the horizon with Hawking radiation, and somehow this entropy within Hawking radiation becomes infinite if you wait long enough. But if you think black holes are finite entropy, like any other quantum object, you kind of have to cut this off somewhere. And basically saying that this entropy is some number, some constant, then if you could relate the time it takes to travel basically from this barrier, this is the light train, to this boundary, this quantum fuzz, that is related to entropy. And this relationship you have between entropy and time scale is in fact the same relationship I showed you earlier. It's the same as this relationship. So you could basically establish a relationship which is rather universal between time of echoes, temperature, and entropy. And in fact, we were not the first to find this relationship. Is this gentleman, actually, well, sorry. I think the order of this got mixed up a little bit. We were not the first to find this relationship. Okay, so let me just show you this observational status, and then I can, I'm going to show you who else got this relationship first. So we went and looked for these echoes in data. This is work with Jahid Abedi, who's been spearheading this direction in LIGO data. Most of the LIGO events, there are like 40 or 50 of them, which are available at the time, don't show evidence for echoes, either positive or negative. They're basically consistent with no evidence. There is one event, which is the biggest event that LIGO observed. This is like the weirdest event you can find, because it doesn't really fit the data very well, doesn't fit any of the models. But it actually does show these echoes. At a significance which is substantial. Okay. So it could be substantial. In fact, there are two of them. Now, it's a noisy data, so it's not 100% proof. But if there's other junk in the data as well, that could be just completely consistent with noise. But in this frequency time diagram at the right frequency and the right time, there seem to be basically echoes as distributed. That now you may wonder, but these other guys, well, this one, it just seems that these echoes are too big to be detected. That's why it's not positive or negative. And they are basically around zero. But most other events, as I said, there are other groups who look for echoes. So this is from the LIGO collaboration who kind of picked up this effort because we suggested we should be doing this. They also, for individual events, don't see evidence for echoes. So these are basically all consistent with no echoes. And this is a slightly dated review of various searches for echoes. Some of them find evidence at, I don't know, 2 to 3 sigma. And many of them also don't find it. There could be, and the reason really is that there are just different methods. And these are big signals. But what I want you to kind of take away from this story is that the echoes to LIGO, in some senses, like the Higgs 2 large hadron collider, well, let's see. So they basically a parallel between these two. If you want to respect all of these tenets of physics, if you want to have the entirety of quantum mechanics, if you want to have effective field theory, which is basically a way to understand quantum mechanics in these largest low energies in a continuous space-time. And then the last one, if you want to respect the gauge symmetry of these two theories, in a standard model, we know that gauge symmetries, SQ3 cross SQ2 cross U1. In gravity, is diffeomorphism invariance, which leads to this holographic description of entropy. If you take these three seriously, then something must be happening at the horizon, and echoes will be direct evidence for that. We take the direct proof of that, which is basically the same argument for Higgs. And if you want to respect these three, something should happen at the weaker scale. And of course, we discovered that that was Higgs. Of course, the echoes, we are not quite there yet. The future is bright, so that even though currently we don't detect them, these are actually simulations or attempts to simulate these echoes. And this is with Susan Ma, who's a postdoc at PI, and Chingwen, a former student. And it looks like currently, from this model of Boltzmann or stimulated Hawking radiation, you expect like a 1 sigma effect, which is at least for some of the LIGO events. This is like a first LIGO event. So it's not as surprising that we haven't seen them, but the next generation of gravitational wave detectors, you expect a 10 sigma detection. These are there. So if they are there, they're going to see it. If they don't see it, it's ruled out, but it's not there yet. So that is there. And another breakthrough in the topic is that they can now actually simulate black holes with quantum membranes around them. The quantum is in quotation mark. So this is work by my PhD student who just finished his thesis of the defendant's PhD, where you could actually have these echoes in full numerical relativity. This is in 1 dimension, this is in 3 dimensions, where you have some membrane which basically reflects gravitational waves. So hopefully when this program kind of it finishes, we could actually have measure of 2 of these membranes with the right properties and see basically and kind of study their echo properties in full numerical relativity. This is in fact the same thing with a spinning black hole. So you could see the effect of a spin on reflection. And again, this is full numerical relativity with a membrane that sits outside the horizon and does the reflection. Okay, so the last thing I'm going to say on this topic is, and it's on the top of observations, that you ignore all the equations here. So let me actually go. This question of can we see it in these images of black holes? And again, you just ignored all equations. The only thing maybe I want you to take away from this is that we could establish, and this is work in preparation, which you could write Farage, who's a postdoc in Waterloo, we could establish a relationship between this so-called Q parameter, which quantifies deviations from Kerr geometry, in terms of the shape of, say, EHT images, related to the time of echoes, which is related to log of energy. And this Q parameter seems to be of order of a few percent. That suggests that it would be of order of a few percent deviation from Kerr geometry. Now, it's a target. It looks like we are decades away from measuring that from this type of images because of also the astrophysical uncertainties, but it's a target that you could look for. And yeah, I mean, I think that's another way of testing this proposal. So let me just go forward. So if you think all of these sound too crazy, I'm not alone. There are people in this room, for example. Kevin is pushing for ideas of weird black holes. There's another one you may not know. In fact, Hanmei, who couldn't make it here, who's my official host, he also proposed and kind of pushed to this idea that basically there are so-called black stars, and there could be even gamma rays coming from these outer boundaries of these. So a lot of people who have talked about this think that maybe the black hole is not the end of the story. It's the beginning, and then there could be near horizon modifications that we can go and look at. Okay, so usually go for 15 minutes. Right, so I have 10 more minutes, I remember. Okay, very nice. Are there any questions so far? So I'm going to kind of start switching gear more to theory, but I'm going to tell you kind of if you find these echoes, then what do they tell you about black holes? And remember that time scale I told you that how can I derive for if you want that relates time and entropy and temperature? Turns out that we were not the first to do it, and Sekino and Susskind in very different contexts. This was before gravitational wave was discovered. They actually thought about this time scale and they call it fast scrambling. In fact, there has an argument for it, just based on your quantum mechanics, that was suggesting basically the faster that can scramble information in a large system, it grows logarithmically with the number of degrees of freedom of that system. And they propose that black holes actually saturate that inequality. So surprisingly, we basically found that indeed, from very different arguments, we recovered the same formula. And in fact, my students, my former student now postdoc in Santa Barbara, showed that these two are exactly the same in very different situations. So basically, this fast scrambling that people derive in the photographic context in the DSCFT is always the same as the time echo time scale for gravitational waves, which is basically this log of radius over pi times or log of entropy divided by 2 pi times. So there's something that's special about this time scale, and I think it would be wonderful to look for it in various contexts. In fact, I should say, even in the cosmological context, there have been papers on this that happen, but I'm not going to talk about them. But the time scale even may play a role in cosmology. Now, what's the quantum black hole? Now that if you establish that there's no horizon and there are echoes, what's replacing the black hole? There are different proposals. I'm just going to run a few for you, and these are all kind of very speculative, but that's the nature of theoretical game. The nice thing is that we could look for signatures of these if there are no horizons. A popular one is so-called fuzzballs. These are kind of visualizations in string theory that don't have event horizons, but they're kind of all higher dimensional, and there are many of them. You can get arcing radiation from these fuzzballs, even though they don't have horizons. There are other types of instabilities, and they could account for the entropy of the black holes. So again, my friend Samir Matur worked a lot on this. Is kind of championed this program. So a couple of new things that we just it's very hot off the presses. So if you do have these quantum black holes, one thing that we suggested that maybe you could simulate them on the laboratory. And we suggested this thing called smart holes. Some of you may know about dumb holes, which are basically a proposal by Bill Unruh to simulate Hawking temperature or Hawking radiation in laboratory system. So we kind of showed that we could also make what we call smart holes, which have both the right temperature and right entropy. And we could get them from kind of smarter things like this, basically these hexagonal lattices. So what Jiao Yang in particular, my former master's student, not PhD student in Waterloo showed was if you take these lattices and then you kind of play a little bit with the couplings, you could actually tilt the light curve such that you make a horizon. And then when you do make a horizon, when the light curve is still, there is somewhere just in the some part of the Fermi surface we call Fermi puddle that has most of the entropy of the electrons, and that entropy is in fact very close to the black hole entropy. So it's the same property as the black hole entropy. So why this matters? Maybe we could actually, even if it, well, it may be complicated to discuss whether there are black hole echoes, but may take some time. But maybe you could actually simulate them in using quantum computers or quantum systems. Like if you could design an analog of a quantum black hole in this kind of analysis. So again, it's a pie in the sky, but some idea. Another idea in terms of what it could be inside the horizons, we use asymptotic safety as another proposal for quantum gravity, an alternative to string theory. And we found solutions which don't have horizons, and they have kind of a scaling binary cores, and then they could possibly lead to echoes as well, because there's no horizon. And again, just hot off the presses, this is yet another proposal for quantum gravity. This is called quadratic gravity. When we found scalar solutions for this as well, the funny thing about these is they have complex insides. So this is what we Gordon Liu and John Quinten, and we found very weird things. Your space-time becomes complex inside these guys. What that means, we don't know, but I think it's a very curious, weird thing. Maybe the way to understand inside the black hole is complex space-time. Okay, so that kind of concludes my foray into exotic black hole. So in the next 5 or 10 minutes, I want to bring all of this together. And I want to convince you that maybe we have a cosmic illusion of causality. And again, I'm going to bring possible observational avenues to test the crazy ideas for the Troy. So this is kind of my laundry list of all the problems with relativistic causality, and then we should kind of abandon it. And in Big Bang, I told you about the horizon problem. The universe appears to be uniform on super horizon scales, but also you have this super horizon scale invariance and very large scales. So, I mean, inflation is a way of solving it, but I told you why we don't like inflation. Maybe causality is the problem. If you don't need inflation, we just need to fix causality, and then that problem is solved. Completely independent inflation, there is the black hole information paradox that I was telling you about. That requires some violation of causality somehow for information to get out of horizon. We have the cosmological constant problems. Exactly how solving that has to do with causality, I don't know, but it is a problem that's based on relativistic causal field theory. We have the Bell's inequalities that suggest a non-local realism, that means basically instantaneous communication or non-local hidden variables. If you want to interpret quantum mechanics in a realistic, in terms of probabilities. So that would require some version of violation of causality. It's not one that you could send information with, but it's still a different type of violation of causality. This is why Einstein didn't like quantum mechanics. And finally, of course, we have the mother of all problems that quantum gravity, as we know it, is not reversible. So maybe we have to fix causality to make it renormalizable. And so basically, these are some random words I put there, but I think maybe we should just revisit all our fundamental principles, like Lorentz symmetry, that UV and IR are independent. So let me just skip this. We could actually see if there is Lorentz symmetry is broken, if there is a preferred frame. So we have a suggestion that we could actually look at we could send clocks on a space on orbital atomic clocks in basically the solar system, and if they're coupled to some preferred frame, this one Lorentz symmetry, you could actually measure that. So this is work a couple of years ago now, last year now, and I think this is very doable. We don't know exactly what the target is, but at this, I think that's an interesting new direction to look for this causality question. But maybe more to the heart of this problem, I told you the mother of all problems is quantum gravity. There is, in fact, a proposal to solve or renormalize the quantum gravity. It's known as Buchalter gravity or Buchalter gravity, which violates the symmetry at high energies. And it turns out that this actually has also, even though you think it's for high energies, in fact, it has a prediction for low energies. And it has a unique prediction with a single parameter in low energies. If you assume no new degree of freedom and no new scale, what it does in this theory is it makes G Newton on the small scales different than G Friedman or on cosmological scales. So instead of one universal constant of gravitation, we have two universal constants of gravitation. One for larger scales, bigger than horizon, and one for small scales. And this is something that directly falls out of this proposal. This is so-called little lambda problem for those of you. Little lambda. Now, there is a crisis in cosmology. There are different things that we measured on flight mass. We might have seen this Hubble tension. And we actually showed that this cosmic Lorentz violation that changes to make these two G's different would actually basically goes in the direction of solving this Hubble tension, depending on which data sets you look at. The Hubble tension is the difference between the Hubble that measures from CMB and the one that measures from supernovae. But in fact, in this context of this cosmic Lorentz violation, you would push these up to values that's consistent with basically. If you the blue region will be pushed up here to be coincide with the pink region. So there might be some tentative evidence for this, and also it could also help with so-called escape tension. So the dashed region and the blue region are very inconsistent. If you look at this theory, which basically allows for cosmic Lorentz violation, they actually become much more shallow. And these are kind of various measurements of this cosmic Lorentz violation with different data sets. And even most recently, you have the DESI data set, and they all kind of seem to prefer a value that is in 2 to 3 sigma microns. So it's interesting. I'm going to skip this. And the last thing I'm going to tell you is that there is, if you want to push this cosmic Lorentz violation to early universe, there are in fact predictions for the bispectrum or non-Gaussianity, and then for the tilt of the power spectrum, which is the star that you see here. And these can be tested in future experiments many of the people in this room actually work on. But it's a target, it's a unique target, very interesting target. If you're interested in cosmological observations, this is something that could give you a target for you to move for. And it's concrete, again, it's one of those things that if it's ruled out, then the whole theory. If you go and then either your measurement is not consistent with this point, or your non-Gaussianity is not consistent with this shape, then your theory is ruled out. I'd be upset, but you have one less theories to deal with. So that's good. Okay, so as Damien mentioned, these are all contentious things I'm telling you about. If you're more interested about cosmic controversies, specifically about the Big Bang, but also the black holes, and all the crazy things that could happen from the Big Bang until down before the Big Bang or into the future. We have a book coming out in May. You should read it. It's exciting. It's with me and a YouTuber, Phil Hopper, who's interviewed lots of cosmologists. All the juicy details, to the extent that editor allowed that we wouldn't get sued, we put all of them in this book. So go read it. Okay, so my conclusion slide, and I promise this is the last one. Of course, you're welcome to continue the discussion, but I want to kind of put it to you, and I don't know how convincing I was, that perhaps the greatest trick the universe has ever played on us is the illusion of causality. The causality could be just a classical artifact, and fundamentally, in a quantum theory of gravity may not exist. So maybe if you realize that and try to make our peace with it, we can solve all these conundrums. The black hole information paradox. If its causality is violated, we should find gravitational wave echoes and possibly quantum pairs in measures of black holes. What that means for what lies beyond the horizon, it's your imagination as good as mine, but I have lots of ideas, and hopefully if you can see them, we could confirm one of or some of them or rule out most of them. But then you don't have to stick to the black holes. You could ask about the cosmos. There could be cosmic Lorentz violation in what people think in dark energy observations. There is one parameter that if you kind of include it, you could actually ease these cosmic tensions. You might even see evidence of it in these quantum sensors if you send atomic clocks in space. And finally, the Big Bang could be different, could be much more peaceful place in terms of you don't have to invent a new theory like inflation. You could just use this quantum theory of gravity, and which doesn't respect Lorentz symmetry, something like Buchalter gravity, and maybe have a specific prediction for tilts, which deviation from a scalar variance and Gaussian. So I know. I mean, for some of you, some of the stuff I said was easier to follow, others might be harder. What I like to lay the foundation or the seeds are is that there are, the hope is not lost. There is hope. There's a crack. And then if we could look through it, there could be all these various observational hints to have the right theory. And hopefully that's how the light gets in. Thank you. Yes. Yes.
Somehow, I mean, are there both in the different classical effects could be through some techniques?
Well, you could just by hand put modifications of structures or curve near horizons, and then there would be records. But it would be kind of ad hoc. You could just put something by hand. Just from the purely classical perspective, there wouldn't be any motivation for them. That doesn't necessarily stop you from looking for them. And a lot of chronological searches in gravitational waves is just by adding things by hand and say, okay, so these are evidence. A lot of things in cosmology or particle physics look like that. But if you want for some kind of foundational motivation, then it comes from quantum mechanics. But then otherwise, you could put these. It's hard to justify them because if you don't satisfy, it's not a solution of Einstein equation. If you just modify it now. You could come up with a new theory of gravity, but again, why it could be said, it doesn't have to be in the time length, it could be much farther out. In principle, much farther in, although I wouldn't trust anything much farther in because if it's a smaller scale than Planck, then you don't necessarily trust classical physics. But yeah, I mean, we could have a neutron star, for example. You don't expect echoes from neutron stars. There's a different type of object. No, I see, I can understand your skepticism that maybe it's just classical that you could look for this. And I think this is perfectly fine that you could look for could invent deviations from Einstein gravity of source and shape and look for them. But in some sense, there is an infinite space out there. And if you want some theoretical guidance, this is one. But otherwise, yes, there are infinitely many things you could look for. How do you decide what to look for? Okay, thank you. Yes.
So this kind of follows on from my earlier question about in.
Yes.
So in quantum physics, the reflection coefficient is basically you have like a wave coming into
Yes.
a well, and you relate the incoming temperature to the outgoing.
That's right.
But it seems like the gravitational waves bring down phase are all outgoing. So how can you reflect all through the event horizon if they're outgoing?
This is a good question. I think what's outgoing is far away, if you want to stay far away. But then if you're near the horizon, there are stuff that's coming after the merger happens. In fact, so I guess I can go back. Let me go back. I think this picture would do. Okay, so basically when black holes merge, there is this basically picture of ring down where there's something that come out and something's fall through the horizon. So these things that are falling through the horizon, that's what I call incident radiation. So it's not something that comes from infinity, but it's something that's as the two black holes merge, it's kind of the end of the ring down. So some of the stuff are coming out, some of the stuff are falling through the horizon. Now, the idea is that classically, this would just continue ad infinitum. Basically, they go fall into the black hole and nothing special happens. But if black holes are quantum, there's some quantum structure here. And then this infalling stuff is going to start interacting with this quantum structure. And that leads to this stimulated emission. So that's the idea. Okay. Yes.
So this is kind of an academic question, probably. Stimulated Hawking radiation, and in principle, one could expect
Yes.
in principle, right? They realize the Colloquium.
No, this is a perfect question. It's and there is no reason to be ashamed of academic questions because we are in academic environment, so we can ask academic questions, absolutely. But in fact, the key has to do with this frequency question. It turns out that in most realistic scenarios, like for photons or for neutrinos, we cannot get frequencies that are comparable to Hawking. For photons, basically, there's so-called plasma frequency, which is almost always bigger than the Hawking temperature, and has to do with the density of plasmas. So that's the minimum frequency that you could access in for photons. And for neutrinos, they have neutrino mass. Now, there could be one massless neutrino in principle. So maybe that could be an interesting question for massless neutrinos. But for massive neutrinos, yeah, this is the same problem there. Yes.
So we can potentially observe the activities now for ground-based detectors, like LIGO, for example.
Yes.
What about like next generation, like space-based detectors, like your supermassive?
So I didn't show anything for Lisa. No, indeed, for Lisa and for even also timing arrays that are right now the way we see or we hope to see gravitational wave from supermassive black hole. So the same story goes. So everything you see here is basically there's the time scale. The time scale, it just scales with the mass, and the amplitude is basically the same. It's this ratio of the amplitudes, doesn't care about the mass of the black hole. So the whole picture, essentially, except for this tiny logarithmic dependence, the whole picture is the same. There are predictions for seeing Lisa echoes with Lisa, so that's similarly strong. So if Lisa applies, that would happen. The pulsar timing array, that's another interesting direction because there's a discrepancy with pulsar timing array. It looks like the amplitude of pulsar timing array gravitational waves is off by maybe a factor of 2 to 5 from what's expected from supermassive black holes. So that's another interesting direction, and maybe echoes is related to that. But yeah, I mean, certainly that's another thing that people are starting to work on.
All right, well, let's thank Niayesh again.